All right, so the next unit is all about chi-squared. We're going to learn 3 different types of chi-squared tests. The first of which is a goodness of fit test. Then we'll learn about a chi-squared test of homogeneity and a chi-squared test of independence. The goodness of fit test applies to a different circumstance. Right? We've already dealt with categorical variables and inference with our 1 prop z test, our 2 prop z test, and the associated confidence intervals for both. But what happens if the variable is not binary? So what if we have a categorical variable and we have many different categories? We don't have a way to see if those proportions differ from some sort of expected or claimed proportion. So this is where our chi-squared goodness of fit test comes in. We're going to test to see if one or more of the proportions from categories differ from expected or claimed proportions. Sometimes we'll want to see if all the proportions are equal, and sometimes we're going to see if they differ from some sort of predetermined expected proportion. So we're going to start this off just the same. We're going to state our null and our alternative hypothesis. And these always work the same way. We can write this such as pi 1 equals pi 2 equals pi 3, etc., right? If we wanted to compare many and we expect them to all be equal. Or we can write out the specific proportion that we'd expect them to equal. Okay? And then the alternative is always the same. At least one of the proportions differ from the claimed proportion. We're just proving that at least one differs. And one of the kind of caveats is, if we know one proportion differs from a claimed one, doesn't that imply that one of the other ones differs? So if one's very low, that has to get soaked up somewhere else. So it does imply that at least 2 of the proportions are going to be different. And we do have our conditions. Write these down, and I gave you that worksheet because we're going to go through those problems, or at least that one problem on there, and you'll see kind of how these expected counts work. So all individual expected counts are at least 1. So expected counts are claimed proportions multiplied by the sample size. So we know that we have those claimed proportions. We can multiply by the sample size, and that's the expected amount that we should get from that sample. And then no more than 20% of the expected counts are less than 5. Essentially, for most of the problems, we're going to look to have all of the expected counts greater than or equal to 5. But if we have just 1, we can still go ahead and conduct a valid test. And of course, we need to trust where the data came from. So hopefully it has some sort of element of randomness, a randomized experiment, or perhaps a simple random sample. All right. Step 3, remember we want to go ahead and calculate our test statistic, which is chi-squared. I think it's easier to look at if you write it like this. Chi-squared, that kind of funny x, is the sum of each of the observed minus the expected squared divided by the expected count. Right? So I'm going to find each of those, and we call each of these values that we calculate the contributions, and then we sum them all together. That gives us our chi-squared test statistic. And then, of course, just like our t-test, we're going to use the number of proportions minus 1 as our degrees of freedom. So however many different categories we have, we subtract 1 from that. So if I was using, say, 1/3, right? The degrees of freedom would be 12 minus 1, or 11. Since it's 12 points. All right? So I'll show you how to calculate test statistic by hand first, and then how to use the table to go ahead and look up the p-value, and then we'll use our calculators to go ahead and calculate both of those as well. And then step 4 our conclusion. Okay? We're going to conduct this just the exact same way we've done every other hypothesis test. We're going to find that p-value. And remember, if the p-value is less than your significance level, we're going to reject H naught, meaning we found statistical significance. The same way we've been doing tests all. The nice thing about the chi-squared test, there's no associated confidence intervals for this entire section. You don't need to decide whether or not it's a confidence interval or a hypothesis test. Chi-squared, it's always going to be a hypothesis test. All right, let's try an example. So a school district in a large suburban area is trying to determine if student absences are distributed equally throughout the school week. Choosing a 5-day week at random, a researcher surveys all the schools in the district and comes up with the following data. All right, so the first thing we're going to ask when we're deciding which type of procedure to use is, do I have a categorical or quantitative variable? Is this categorical or quantitative? Categorical, right? We're talking about day of the week. What makes this inappropriate for either a 2-prop z-test or a 1-prop z-test is, notice I have 5 different proportions I want to look at. Okay? And the question I'm answering is the true proportion of absences different from on one day of the week from any other day of the week? So let's go ahead and state our procedure. This is a chi-squared. And for goodness of fit test, we can just write GOF. And that's chi-squared. Goodness of fit. So let's start with our null and alternative hypothesis. So in this case, we're starting with our status quo that all of the days of the week have the same proportion of absences. IM equals IT equals IW equals IR. And then our alternative at least one proportion differs from the others. And of course, I'm going to define my parameter of interest by Monday through Friday. The true proportion of all absences for a day of the week. So step 1 done. I don't have a significance level, so I'm going to choose a 5% significance level. The next thing I'm going to do is verify my conditions. And to verify conditions, I need to have my expected counts. So here's how we can go ahead and calculate those expected counts. I have a total of 305 absences. Since I believe all of the proportions are equal, the expected value for each of these days, I can just divide by the total number of categories. Okay? And this works when we have a null hypothesis where they're all equal. But if we had some predetermined, like we thought, say maybe 25% of all the absences occur on Monday, right? We'd multiply that value by 0.25 and the other values by the associated proportion of our expectation. So in this case, each of our expected values 305 divided by 5, it's 61 for each. So now we can go ahead and verify our conditions. We have our simple random sample, and that is stated in the problem. And 2, all expected counts are greater than or equal to 5. Step 3, I want to calculate my test statistic. So remember what we're going to do for each of these, right? Remember our chi-squared test statistic? Yeah. The sum of all of our observed minus the expected counts divided by expected. So let's figure out what the contribution for each of the days of the week is. So Monday, we have 73 minus 61 divided by 61. Remember that top is squared. Tuesday, we have 57 minus 61 squared over 61. Wednesday, 48 minus 61 squared all over 61. And we have Thursday, 59 minus 61 squared over 61. And then Friday, 68 minus 61 squared multiplied by 60. All right, so these are the individual contributions to our chi-squared test statistic for each of the 5 days of the week. The R stands for Thursdays, and I already used T for Tuesday.
Let's say TA.
All right, so in my table up here, I'm going to write down each of these contributions. So I'm back up here. And I get 2.36 for Monday, 0.26 for Tuesday, 2.77 for Wednesday, 0.07 for Thursday, 0.8 for Friday. And then my chi-squared test statistic is just all of those added together. 6.26. Now I have my test statistic. The next thing I want to do is find my p-values. So my chi-squared, 6.26. Now my p-value. I can use a table, the chi-squared table in the back of our book. And you're also given a chi-squared chart on the AP test as well. All right, so once I have that chi-squared, I want to find the p-value. I'm going to go ahead and go to my chi-squared chart. And the way this works is I have my degrees of freedom. In this case, what were the degrees of freedom? 4. So I go down here, and then I'm just going to go across the row, and I find right over what two values is 6.26 in between. So it's in between right here, between 0.25 and 0.1. So I know my p-value is greater than 0.1. So that's going to lead me to fail to reject. So I know my p-value is greater than 0.1. Let's go ahead and find the exact. So we found our p-value equals 0.18. And 0.18 is greater than 0.05. So I'm going to fail to reject H9. All right. And then our conclusion. At the 5% significance level, there is not sufficient evidence to say that the true proportion of absences on one day of the week differs from any other day. So the next logical thing to ask is this, right? If we did find statistical significance, what we want to know is which one of those days of the week had the highest or lowest proportion, or which one differed most from the expected. We can find that by looking at the contributions. So those contributions are important in that it tells me which one affected our chi-square test statistic the most. So in this case, I can look and say, Wednesday seemed to differ the most from the expected value, right? And therefore had the largest contribution. Please like this video and put some sort of comment.